Hey guys, welcome to lesson 8. We're going to talk about excited state versus ground state for electron configurations and how to distinguish between the two. Alright, let's go ahead and get started on page 23. Notice on page 23 we have neon and neon, both the same atom. There's nothing different about the number of protons. Number of electrons, if we count them up, they're the same. There's 10 electrons here, there's 10 electrons in both of them. Alright. So that's not a problem, but the configuration of the electrons is different. And the electron here, this outermost electron, you'll notice is in the third orbital. And that third orbital is a higher energy state, we call it. And so it actually has what we call an excited state. And that's about what there is to it. I'm going to talk about how and what causes that, and then how we can deal with notations. Ground state. Bye, Nora. Ground state is electrons and the lowest energy configuration. So we just want to remember lowest energy means closest to the nucleus. It's the configuration that's always found on the periodic table. Now I use abbreviation for periodic table like this, periodic table of elements, PETO. Sometimes I just want you to be aware of that. Ground state electron, so don't forget. I should write this down because some of you will be watching it without the sound, which is not a great idea, but I should help you out. Ground state electron configuration for lithium is 2-1. That makes sense. How about the excited state? Well, for electron configuration for lithium, it could be changing from 2 electrons in its kernel, which means its core, to 2 electrons in its outer shell, its valence shell. And that's different than the 2-1. So what happens with the electrons? This is excited state is when the electrons are found in a higher energy level. And we call this a configuration again because it's the way things are arranged. And again, it's not found on the periodic table. So it's not the periodic table configuration. All right, distinguish between ground state and excited state configurations below. Well, you'll need your periodic table for this, and you'll see that they give you what we call the Bohr electron configuration. So again, Bohr electron configuration for this one, we have our nucleus, which we have a first energy level and a second energy level, and we have, let's say, 2 electrons and our kernel electrons and 1 in the valence. This is considered the ground state because electrons match the configuration found on the periodic table. If you look on the periodic table for an atom with 3 electrons, which is lithium, it is definitely not this configuration. It's 2-1. That's why we call this the excited state. All right, here's an atom with 3 electrons. Now it's configured 1-1-1, which definitely is not. So we consider that on the excited state. 2-7-3. You'll notice you'll have to look on the periodic table for a 12 electron element, and that 12 electron element will not have this configuration. I guess I could have thrown it up there, but that would be magnesium. The magnesium configuration is 2-8-2 on the periodic table, so that's the ground, and this is the excited state. I hope you're catching on too that this 8 in the second energy level is a ground state configuration. Now 2-8-8-2, all you have to do is look for that configuration on the periodic table and you'll see that's calcium. It takes a while for you to scan through it, but because it is found on the periodic table, we know it's a ground state. Now this 2-8-17-6, that is a harder one to see, but there's a pattern here that you'll see on the periodic table as you look at these higher numbers, and that is that third number sometimes is 18, but it's never 17. as long as if there's more electrons left. So this by far is an excited state. 28818, that matches our ground state configuration. 26818, the key number here that's wrong is the second number on the periodic table is always 8 when it's filled, and this number is 6. So we know it must have electrons that are shifted. Over here, 258, this number should be 8, but it's 5, so it's also the excited state. All right, hopefully that helps. Let's move on to some concepts. The greater the distance from the nucleus, the greater the energy of the electron. So the more energy an electron has, the more it will push out. When ground state electrons absorb energy, so in a ground state, a boring, just normal, everyday electron somehow finds energy in the universe, a light wave hitting it, flame, and it absorbs energy, they jump to a higher energy level, or what we call an excited state. This is a very unstable position, though, which means as soon as it loses its energy, it's going to drop back. So it's a very temporary condition. The excited electrons, now that they absorb the energy, are shaking around really fast up there in this high energy state. They rapidly fall back down. Or drop to a lower energy level. Now, something special happens when things drop, when electrons drop to an energy level. The excited electrons fall from an excited state to a low energy state. They do what we call releasing energy. Now, energy you might not think of it as, but color that you see coming from a flame is light energy. And the type of light that is emitted depends on its frequency, and the frequency depends on the atom that it's releasing. So when we go from ground to excited, what's happening? Well, it has to be gaining energy. Energy is absorbed. Now, there's a special thing that is produced, and you'll see it down here. As the energy is absorbed, all of a sudden a frequency of light is missing. It creates what we call a dark line spectrum. And it's pictured down below, right here. And then, and a dark line, so that's good. Now, when we release that energy, and let me draw a picture over here because I think it makes a little more sense. I'll draw a nucleus, and then I'll have the first orbital, and then I'll draw a second orbital, and then I'll draw the electrons. Now the electrons here are in the ground state, and we'll have another electron, let's say, no, we'll just keep that electron. Now what we have here is we'll add light energy or flame. Hi girls. And then we have a light energy. Here, let me just pause this for a second.